I'm interested in the history of physics a little bit, and so I thought to myself, what is the first really modern question that, that anybody asked that has to do with the cosmological constant? You're the one who said cosmological constant. In fact, I heard you say, are there alternative theories to lambda? And then in the next breath, you said, are there alternative descriptions besides anthropic to the cosmological constant problem? I take it to mean that you think it's cosmological constant. But the first real reference that I know to it was a conversation between Pauli and Dirac. It was sometime in the 30s. I don't know exactly when. And they were talking about the infinities of quantum field theory. And Dirac said the vacuum energy, the zero-point vacuum energy, comes out infinite, and therefore it can't mean anything. And Pauli turned around and said, just because something is infinite doesn't mean it's zero. This, very funny, very humorous, but very sharp, very smart. And it is basically the question that has dominated the dark energy issue for theorists in any case, for at least the last 30 years. So I'm going to give you a theorist's perspective on it. I will tell you right now that I don't know any answer other than the anthropic possibility. And I think what is incumbent upon us now is not to argue ideologically about whether anthropic reasoning is sensible or not sensible, but simply to try to confirm it or disprove it, both theoretically and observationally. Very, very hard, but I will talk about it a little bit, as much as I know. These equations you've seen before. They're Einstein's field equations. I don't need to belabor them at all. You all know that Einstein realized that you could put another term into the equations, the cosmological term, involving a parameter lambda. And of course, he put it on the left side. The left side has to do with geometry. The right side has to do with energy and momentum, the sources of the gravitational field. But it didn't take long, and in particular, the conversation between Pauli and Dirac had to do with the idea of putting it on the other side of the equation. On the other side of the equation, the cosmological constant becomes part of the source, and we give it the name vacuum energy. V for vacuum, it could also be V for potential energy, but V for vacuum energy. And we understand today that a vacuum energy could be the source, and not only could be, but should be the source of the accelerated expansion of the universe. What is surprising about the existence of a cosmological constant? Nothing is surprising about the existence of a cosmological constant, as I'll explain. What is surprising, and very surprising, is how little dark energy there is. Not that there is dark energy. The press gets it all wrong. They say, what is this mysterious dark energy? The real question is, why is this mysterious dark energy so very, very small? Okay, let's just review for a moment what dark energy does. Lambda meaning the cosmological constant, dark energy, vacuum energy, all the same stuff. First of all, it enters into Einstein's field equations, which for a simple cosmology, FRW, cosmology is just the standard FRW equations with lambda on the right side. And as you know, I'm sure most of you know, or all of you know, that the energy density term rho for ordinary sources of energy decreases with increasing scale factor. A is the scale factor. The curvature term k over a squared also decreases with increasing scale factor. The only term that doesn't decrease is the cosmological constant term, and so it dominates when the universe gets big. You can throw everything else away, solve the equation, and what do you get? You get exponential expansion. And so the existence of a dark energy should imply an exponential expansion. In fact, the first I heard of the problem came from David Finkelstein sometime around 1967. he explained to me that if you took all the dark energy or all the vacuum energy that comes from scales up to about the electron mass, the vacuum energy, he didn't call it cosmological constant, the vacuum energy would be such that its gravitational effects would curl the universe up into nothing much bigger. I can't remember if he said the orbit of the moon or the size of the moon. This is something we could work out, but a very small universe. So we have a puzzle. Where is the dark energy? Why isn't there dark energy? Now let's take a theorist's view of it. The theorist's view of it is that vacuum energy, the right hand, putting lambda on the right-hand side, comes from various quantum field theory processes. The first kind of process is basically classical. Oh, does this thing work? Let's see. I'm not sure which one to push without, I don't want to switch the slide. Good, okay. Right. The first one is the classical contribution. It could come from any sources of classical vacuum energy, classical, whatever it happens to be, a bare cosmological constant, a field potential, whatever you like, no loops in it, no quantum mechanics. But whatever it is, there are corrections to it, radiative corrections, Feynman diagrams. And the problem is, as Dirac correctly perceived, these Feynman diagrams are all infinite. So the vacuum energy in quantum field theory, which has every reason to gravitate, is infinite. How do you actually make some sort of systematic calculation? Well, to make a calculation, you have to regulate the theory, cut it off, introduce into the integrals that go around these loops here. Oh, incidentally, one important thing here is that bosons contribute positively to the vacuum energy, fermions contribute negatively, and in general, mixed diagrams of arbitrary complexity may be positive or negative. If you cut the theory off, if you say the end of the integrations occur at the largest mass scale that we know makes sense, namely somewhere around the Planck scale, and you don't have to believe that, that's a theorist prejudice, then you would find that the vacuum energy, it's quartically divergent, and therefore its order, the cutoff to the fourth power, times some function of the coupling constants, whatever they happen to be, mass ratios, dimensionless quantities. This function begins with the number 1 in perturbation theory, just these diagrams here. Pluses and minuses, of course, for bosons and fermions. And therefore, the expected answer, not expected not by observation, but expected by a theorist who knew no better and just made this calculation, would be of order the fourth power of the Planck mass, and of course, that's an absurdly large number. On the other hand, the actual observed cosmological constant, I should go back a step. Oh, it doesn't appear on here, but let me just say what this would mean. What it would mean is that the time constant for the exponential expansion of the universe would be about 10 to the minus 42 seconds, okay? Universe doubles every 10 to the minus 42 seconds in a pure theorist's world. On the other hand, the observed universe doubles in a scale of order time 10 to the 10th years, which I like to call one Darwin. I call it a Darwin because it's about the time scale for intelligent astronomers to evolve on in the universe. And I think it's a good unit of time, a good name for a unit of time, particularly for those people who have anthropic leanings. Okay, here it is, right here. Right, so that 10 to the 10th years compared to 10 to the minus 42 seconds translates into the statement that the vacuum energy is about 10 to the minus 123 times m Planck to the fourth. In other words, we have a very, very serious fine-tuning problem where the sum of all these graphs, each one of which is of order 1 times m Planck to the fourth, is adding up to something 123 orders of magnitude smaller. One possibility is we're just making a basic mistake. We're not understanding. Dirac was somehow right, except not quite right. The other possibility is question mark. We don't know. I don't believe this problem can be discussed reasonably as simply the dark energy problem. I believe it must be discussed in a bigger context. The bigger context to include, I think, the entire history of the universe. And so here's the short form of the history of the universe that will serve us very well today. There is a potential energy function as a function of some field, potential energy as a function of field. You all know the picture. It's the inflationary picture. And for reasons unknown, this inflationary potential had a flat range over here, pretty flat. The universe slid down, exponentially expanded along here because the vacuum energy was more or less constant, went over the cliff is called reheating, and plunged down to the bottom. The bottom is not quite at zero energy, it's at this 10 to the minus 123. That's the short form history of the universe, and almost everything that we observe, I take it back, just about everything we observe, all occurred either down this slope here or very, very close to the bottom. Okay, that's the history of the universe in a nutshell. Two periods of exponential expansion, one with a time constant of, for inflation, it's possibly about 10 to the minus 32 seconds, down here, 10 to the 10th years. I think that's the context we should think about it in. There are other possible explanations of accelerated expansion. One of them is called quintessence. I hate it, I dislike it intensely, but nevertheless, we should think about it. It's the idea that the potential doesn't have a minimum, it just slowly slides down to zero, and we're on this very, very slow roll here. The problem with this is I think it just exacerbates the problems. First of all, it still requires you to understand why, at the minimum, it's extremely small, either zero or smaller than 10 to the minus 123. But on top of that, it requires a whole bunch of derivatives of the potential to be absurdly small. It doesn't seem to do anything positive for you. It just makes matters worse. The fine-tuning problem for this kind of quintessence potential is worse than for a single cosmological constant. However, I certainly think we should keep our minds open and ask what it implies. Nevertheless, I will not speak about it further. All right, so what is the option on the table? The option on the table is the anthropic option. The idea that the cosmological constant might be determined by anthropic considerations, to my knowledge, first appeared in papers of Banks, Linde, and Weinberg. This is not one paper, this is 3 different papers, and they all had pretty similar ideas. Weinberg's idea was more quantitative, all around 1987. I won't go into it in detail, you probably know it, but let me give you a metaphor for it. A metaphor for what the idea is. I think the metaphor is useful, particularly for people who are not deeply ingrained in the mathematics of inflation and so forth. Here's an analogy. Here's the sea. Here's the sun. And this thing here is a submarine. We live in a submarine. We live in a submarine, a green submarine, not a yellow submarine. We all live in a green submarine. And the green submarine is a rather marvelous submarine. The bottom of the sea is a very dangerous place for the submarine. It will get crushed. The top of the sea also happens to be dangerous. It will get fried by the sunlight, made of some sort of material that gets fried by sunlight. People are in it, and they notice that they've been floating midway between the top and the bottom for a very long time. How long? A Darwin. They've, after all, evolved. They've evolved enough to ask questions. They've been floating in the middle for a Darwin. On the other hand, their submarine is made of all sorts of stuff, carbon, silicon, iron, other stuff, with a very different density than water. Some of it is lighter than water, some of it is heavier than water. By what miracle is it that this submarine just managed to float halfway in between for 10 to the 10th years? That's the miracle that they discover. If it's just a tiny bit too heavy, if the composition is just slightly wrong, they fall. If the composition is slightly wrong in the other direction, they rise. What's going on, they ask themselves. Well, some either smart or perhaps stupid theoretical cosmologists, physicists come along and say, we know what this means. What it means is there's just a hell of a lot of submarines out there. The sea is extremely big. There's a lot of submarines, all of slightly different composition. Most of them in 15 seconds fell to the bottom of the sea or rose to the top. Nobody in those submarines, they're completely empty. A handful of them lasted for an hour. Nobody in them either. Some tiny, tiny, tiny fraction of them was of composition accidentally just right to be able to float in the middle. Those are the ones that have astronomers. That's the logic, if you like. That's the logic of anthropic reasoning. It's no more philosophical. It's no deeper than that. That's the idea. Is it right? That's for us to test, both theoretically and experimentally. All right, what is the sea in which we all float? Let's call it de Sitter space. And let me remind you what de Sitter space is. This de Sitter space is a generic de Sitter space. It's not necessarily the world that we live in today. It's not necessarily the world of early inflation. It's just a generic de Sitter space. A generic de Sitter space is an exponentially expanding space, and it can be drawn on what is called a conformal or a Penrose diagram. It's infinite in extent, in time extent, but to draw it in a way that guarantees that light rays move on 45-degree angles, you have to draw it as if time came to an end. These sequence of green lines here are time slices. This is t0, t1, t equals 2, t equals 3, t equals 4. There's an infinite amount of time, but the causal structure, the geometric structure, is such that it's best drawn in this way here. So let me show you what that does for you. If you draw it in this way, you can immediately see why there are horizons. Why a de Sitter space has horizons. Here are two, oops, I knew that was going to happen. Now what did I do? I went, yeah, okay. Good. But now I forgot what, I see, okay. Two observers. Vertical lines are observers in this world, and they can look back, and they look back at any given time along their light cones. Here they are, two of them. At some time in the past, in fact, their past light cones overlapped. They can see each other rather easily. In fact, any observer up here can see his friend in the sufficient past. But what he can't see after a point, he can't see his friend at the same time. There is an event horizon. This is the black person's event horizon. This is the red person's event horizon. The black person cannot see outside his own light cone. The red person cannot see outside his light cone. Those are event horizons, and this is one of the reasons that it's useful to draw de Sitter space in this way. You see everything that's going on a single map. Okay. That's the background, that's the sea that we live in. Or at least according to a hypothesis, that's the sea that we live in, not necessarily the 10 to the 10th years or the 10 to the minus 42 years, but some sea like that. And the question is, what is the submarine creation mechanism? The submarine creation mechanism is the mechanism that creates pockets of space that we can live in. The hypothesis that most theorists who think about this think of is Coleman-de Lucia tunneling. I will explain that in a moment, but let's come back to a scalar potential. If there's a scalar potential, and it happens to have sufficient structure with sufficient number of minima, a generic function with lots of minima or something like that, then tunneling is possible. Tunneling from one minima to another. This is a picture of what tunneling would look like for a Coleman-de Lucia instanton. You tunnel from one minimum out of that minimum, and then typically roll down to the next minimum. That's the structure of Coleman-de Lucia instantons, and I've drawn here a very generic kind of roll down. That is what one would expect from a generic function with a single extra minimum in it, 2 minima. What kind of cosmology does this lead to? By that I mean, what kind of cosmology does this lead to in the submarine? The submarine is a bubble. The submarine is a bubble that nucleates when this tunneling event happens. The tunneling event is a local event, a small little event which nucleates a bubble. These are the bubble walls. The bubble walls spread out just like the bubbles of gas in a supercooled fluid. The bubble spreads out, and the interior of the bubble is a new environment, the new environment on the other side of the potential. The question is this a good submarine? There are many of them. It keeps happening all over the place. So there are lots of them, many, many different types if physicists' speculations are correct. The question we want to answer is what phenomenological, experimental, observational signals can confirm this? Unfortunately, the list is very, very limited. I know of only 1 or 2, and even those would take a great deal of luck to be able to observe. But let's begin. The first thing is looking to the side, trying to see these other bubbles that occur is hopeless. If we live over here, our horizon precludes us seeing them, period. They are simply outside of our horizon. We cannot see them. So looking to the side, meaning to say looking for other bubbles, similar bubbles, is out of the question. What is possible is looking back in time to try to discover whether there's any evidence of a bubble nucleation, that we were born in a Coleman-DeLucia bubble nucleation. Looking into the past and trying to see our origins in a Coleman-DeLucia bubble nucleation may not be impossible. So the question is, what does a Coleman-DeLucia bubble look like from the inside? Here's a picture of it again, but now I've drawn in some surfaces of constant energy density, surfaces that you could think of and should think of as slices of constant time, not for this all-over external sea, but for the observer on the inside. This takes a little bit of mathematical study to find out what the surfaces of constant energy density look like, but they look like this. What kind of geometry, spatial geometry, does the observer on the inside see? This would be a slice of space. The answer is they see negative spatial curvature. They see an infinite universe. Let's go back. Going from here out to the edges over here on one instant of time is basically moving on a geometry which looks like, I think you've probably seen this before, this is just basically a picture of a negatively curved, uniformly negatively curved, it's called a Poincaré disk, and it's just a picture of negatively curved space, is just moving out to the boundary. The space is infinite. The space is infinite, even though it's a bubble contained in what looks like a finite region. The space itself is infinite, and it's negatively curved. Okay, let's go back for a moment and ask now, again, a little more about what this bubble looks like. Here again, I've redrawn the picture of bubble nucleation with a generic potential that just falls down to 0 like this. Well, a universe born in this way could be called a shotgun universe. It's first of all curvature dominated. It has a lot of negative curvature in the early period. And negative curvature, I thought I had 10 to the 10th years for this. Good. Negative curvature means that the stuff which is shot out is above the escape velocity. Escape velocity for forming galaxies in particular. It's shot out, diluted very fast, it's empty, and it's k equals -1. It's not a good submarine. What do you need to make it a good submarine? You need a period of slow roll inflation to dilute the curvature. If you dilute the curvature, during some period of slow roll inflation, then the production of matter is different. Everything is produced more or less at rest with respect to each other, and there's plenty of opportunity for, okay. How much inflation do you need in order to create an acceptable submarine? That is the anthropic bound on the amount of inflation that you need. If you take the observational bound on the number of e-foldings to be 60, now of course 60 is an arbitrary number. It could be 30, it could be 40, it could be 50, depending on the model. But if you take a model in which the observed bound is that the number of e-foldings is greater than 60, what it says is the anthropic bound is greater than 57.5. Now, the actual invariant number is the difference between the observed bound and the anthropic bound. And what it says is that the anthropic bound is rather close to the observed bound. In other words, that if the number of e-foldings was much less than 60 in this model, we wouldn't be here. It doesn't say that the number of e-foldings couldn't be much greater than 60. All right, here is a typical picture. It's hard to make a lot of e-foldings. You have to tune parameters. You have to make that potential very flat. If you just take a random sampling in parameter space, you find out that the probability for a given number of e-foldings tends to fall rapidly just because it takes more and more fine-tuning to make a lot of e-foldings. And in one simple model, one simple statistical model, the probability for n e-foldings falls like 1 over n to the 4th. It's just hard to make them. So here's a picture now. Here is the anthropic bound of 57.5. Here's the observed bound of 60. And if you ask the question, not what's the probability that you have more than 60 e-foldings, but what's the probability that you have more than 60 e-foldings given that you have more than the anthropic bound? What's the probability that you have more than 60 given that you have more than 57.5? Then the answer is about 85%. All right, so the point is that anthropics, if you like, is the explanation of why there was a long period of slow roll inflation. On the other hand, you could also ask, what's the probability that we have a chance that the number of e-foldings is low enough that we can see back more or less to the bubble nucleation event? That would require that the number of e-foldings was no bigger than about 63. More than 63, everything gets diluted away. And if you use the same parameterization, you find out that it's about 15%. Now, there's nothing hard about that number. It's just a model. But 15% is a small number. It's a long shot, but it's not absurdly small. If we are very lucky, we may be in this region here, and then we can see back. What do we see? The first thing we would see is negative curvature, if this theory is right. That's the most robust prediction of bubble nucleation. Now, I would say the most robust prediction is not that you see negative curvature, but that you don't see positive curvature. If we were to see positive curvature in the next round of curvature experiments, or the next 2 rounds, we would have to go back to the drawing board on this idea. If we see negative curvature, that's good for these ideas. If we see 0 curvature, I know, I'm just about done. 1 or 2 more. There's very, very little. Unfortunately, there's very little. I wish there were more. All right, another thing is about the fluctuation spectrum of density perturbations. The fluctuation of density perturbations, well-known formula, you probably mostly know it. The power spectrum is proportional to, this is V, this is the vacuum energy, divided by the rate of the velocity as you fall down the hill here. And as you come off this hill here, 2 things are true. H squared is bigger than it would be a little bit later on the flat portion, and phi dot is bigger. In general, if you look at reasonable parameterizations, it looks like phi dot tends to win, and the effect is that the fluctuation spectrum at the very beginning of the slow roll here is suppressed. Now, it could be enhanced, but I think the best bet is that it's suppressed, and that would be or low L suppression due to the fact that you're riding down a hill here. This is a made-up picture. I didn't make up this part of the picture. I made up this part of the picture here. I am told that, and I cannot confirm this, I am told that there is a low L anomaly where the best fits to a generic vanilla-flavored slow-roll picture would look something like this, and the data is a little bit low. This, of course, is pie in the sky. This was not after the fact, incidentally. The prediction of a low spectrum is about 10 years old. Forget that. Another fact, that if you look at tensor modes are proportional, the spectrum is proportional to h squared with no phi dot in the bottom. This is an observation that is about to come out, I believe, by Busso, Harlow, and Senatore. And notice that the formula does not have a phi dot, so that if we do see tensor perturbations, they should not be suppressed. In fact, one might say that they should be slightly enhanced at early times because h squared is a little bit bigger. So one of the things you might expect, if you can see these kind of things, is just such a relative enhancement of the tensor spectrum. Finally, what about, incidentally, that's phenomena that would take place in L from 2 to 50, let's say. What about extremely low L? Well, we know that extremely low L is cosmic variance restricted, but still, let's just go ahead and ask what it has to do with. What very, very low L stuff could have to do with is the nature of the critical bubble that forms at the very beginning. If the critical bubble is stiff, if the parameters are stiff, meaning to say that the surface tension is very much larger than other parameters, then the bubble will be very spherical. If the surface tension is smaller, the bubble can be floppy. In fact, there's a whole range of floppiness that goes all the ways to possibility of multiple connectedness and really complicated things. This kind of thing could lead to very, very low L anisotropy. Low L means L of 2 or 3. Those are all of the signatures that I know of. What should we do? We should keep pushing. We need to know whether W is really equal to -1, whether it's a cosmological constant. If we can measure the curvature, great. If it comes out to be negative, we're in business. If it comes out to be positive, we go back to the drawing board. Is there really low L suppression? Well, the only way to find out is to beat back the cosmic variance, and I'm told that there are ways to try to beat back I won't go into them. Tensor modes, very important, and in particular, are they unsuppressed relative to the scalar modes? Finally, there's the question of Gaussian or non-Gaussian, and I haven't mentioned it all because I don't know how it fits into the story altogether. And thank you very much.
I'm an old guy, and I was in graduate school when quantum electrodynamics was divergent, and everything you calculated was infinite.
Right.
And then along came renormalization, and all of a sudden, everything was fine. Now, you haven't talked about the possibility that we don't have it quite right in the particle spectrum and all that. What are the chances that it's really almost perfectly renormalizable?
That quantum gravity is perfectly renormalizable. That would be fine with me. I don't think it is. I don't think there's any chance at all, frankly. But let's suppose it is. It would not explain the problem of why a certain dimensional quantity is so small. It would be the same problem, or a very similar problem, to the problem of the Higgs mass. The Higgs mass in the standard model is perfectly renormalizable, but still perturbations way, way up near the grand unification scale or Planck scale would destabilize it and push it way up. It's not a question of renormalizability. Renormalizability allows you to hide things and just say, forget where it came from, here's the final answer. The Higgs mass is an example where you can see directly, completely renormalizable, but still, there's a real fine-tuning problem. Now, certainly it is possible we just have the wrong idea. It's possible. And I think up until fairly recently, one might have taken Dirac's position. It's infinite, and therefore it's zero. And theorists very much, especially string theorists, tended to say that. Once it was measured at 10 to the minus 123, there was no refuge in saying there might be a symmetry or some theoretical argument that we don't know that makes it exactly zero. So there's this funny number, 10 to the minus 123, lambda divided by the Planck mass force, that needs explanation, and I would leave it at that.
Yeah, may I just make a comment on this? If when, actually, this 123 comes from using the instant form vacuum, which
the what?
Instant form vacuum. In Dirac's language, there's the instant form and the front form.
The 10 to the minus 123 comes from an experiment.
No, no, the 10 to the 100 plus 123 that you quote is actually when you use the light front instant form Hamiltonian and identify the vacuum with the instant form.
Yeah.
If you use the light front vacuum, which is causal and frame independent, then you get zero from QED.
Good. Zero is not so good either.
No, no, but then, of course, you can get another contribution from modifying gravity or the Higgs theory or something. But the answer that you get from quantum fluctuations in quantum field theory in the front form, which again is causal and frame independent, is actually not this huge number.
But you're asking the wrong question. The right question is not really what the vacuum energy is. The right question is how these loops gravitate, how they connect to the graviton amplitudes. And I don't know any argument, one way or the other, well, I don't know any argument that would say that this renormalizes to zero. These are gravitons, this is an electron loop. There's no reason to my knowledge to why this should be zero, light cone front or not.
But actually, we should argue about it, but it really, in fact, is zero because the vacuum in the front form cannot have bubbles. It's already normal ordered, if you like.
All right. Yeah, please.
I think it's a very simple solution to that problem.
Can we thank Lenny again?